Thank you so much, Professor Shin, for the wonderful introduction. It's my great honor and pleasure to be presenting today at the Mobility Graduate School. So yeah, let's get on with it. I am going to be talking about learning patterns for autonomous control towards data-efficient AI and adaptive decisions. Oh, okay, there we go. Yeah, so before here's just a brief interview. I guess I don't need to talk about this. As Professor Shin said, I lead the Autonomous Control for Stochastic Systems Laboratory, and the exact details are going to be talked about in today's seminar. Now, I am Korean, but I was born and raised in the US. But if you do have any questions during the presentation or at the end of the presentation and you feel more comfortable asking in Korean, by all means, just ask me in Korean. Okay, so motivation and overview of what we do comes from looking at the title of the talk. I'm sure most of you already are familiar with autonomous control because there's so many real-world applications in the modern day towards autonomous control, like formation flight, autonomous driving, those waiter robots that you see in the restaurants, robotics. So lots of examples. And in particular, there have been explosive growths in the modern day, particularly towards hyperscale AI, like ChatGPT, OpenAI Figure, Naver's Hyperclova X, Microsoft Copilot, Google Gemini, and Tesla's Optimus. So that's what happened in the recent times, the early 2020s, the AI boom. Recent successive with generative AI models like DALL-E, ChatGPT led to an explosive increase in investment for hyperscale AI. Now, consequently, that needs lots of data and lots of computing because the number of parameters needed to train these models is increasing exponentially. So that seems to be the current solution that is adopted by most industries in the autonomy revolution, like Google, Tesla, Microsoft, Meta, OpenAI, and so on. Their solution is to increase computing, increase data centers, basically increase everything. Now, this solution is wildly inefficient, and I'm sure a lot of you have seen the recent articles that were contributing towards that. Large amounts of data are not always available due to cost, security, and ethical issues. Gathering large amounts of data is also unsustainable because it uses a lot of electrical power. And gathering large amounts of data is also inefficient because less data-hungry methods for autonomy exist, and they can be combined with AI. Now, out of the 3 points listed here, our research focuses mostly on the last point. So here is just a slight categorization of what our lab does. We broadly combine both theory and application to develop data-efficient autonomous control methods based on AI, especially for stochastic systems. So that includes 2 parts: pattern learning, the identification and usage of spatiotemporal patterns for control, and the trade-off between model-based and model-free methods. So how do we learn an approximate model and improve the data efficiency of the model-free part? Just to go into a bit more detail about each of these 2 points. First, for the pattern learning, I would say out of this title, which I'm showing to you again, it's really the patterns part, which is our focus. So patterns in time versus patterns in space. Patterns in time, there's a lot of examples in the real world, like arrival processes, for example, vehicle arrival processes in this underground parking lot here at Caltech. You can clearly see if you plot the data over the time of day, over the time of day of the week, there's an increase of cars that show up in the morning around 7 to 8 a.m. when people come to work. And then there's another slight bump in the evening time when people like to use this parking lot for the gym that's nearby. There's also patterns in space. For example, we have this tiny hexagon over here, which can be mapped over maybe this 2D plane and maybe more generally over this 3D surface. So that also has a large number of applications like space, like satellite constellations over the surface of the Earth, or ground vehicle road networks, which have this kind of spatial patterns in the form of a grid. Okay, now what about the second point, model-based versus model-free? Here is an example from stochastic control. Now, this is the common stochastic differential equation that is used for modeling Gaussian white noise systems. And white noise is, for example, this kind of continuous process that evolves over time incrementally. This is an example with positive drift. Now, you can consider more broad cases where you add this kind of jump, impulsive jump, so it becomes a jump discontinuous process instead of a continuous one. Okay, so why do I bring this up? Well, because the white noise case is pretty well studied in stochastic control theory because of its convenient properties like the central limit theorem and linearity of Gaussian random variables. And it turns out it has a wide usage of applications like localization and mapping and navigation. And as a result, a lot of algorithms have been developed for it, like LQG control and Kalman filtering. These are all broadly model-based sections of white noise control. Now, what happens if we add these impulsive jumps, like what I showed to you in the previous slide? Now, as soon as we get out of this class of modeled systems, so it's out here, we start to rely on end-to-end model-free control via big data analysis and AI. But some of the trade-offs that I mentioned before are persistent here as well. Training for AI and also hyperscale AI consumes too much power, too much data, and especially redundant learning of information that could be obtained from patterns or structured models. So what we can do instead is, these are impulsive jumps, but in the literature of applied math, these can also be modeled using compound Poisson processes. So why not expand the capabilities of model-based control design to encompass compound Poisson processes, and then so we can leave model-free as more of a supplement to add rather than training it end to end. Okay, so here's the slide that we've seen before. This is just a summary of the 2 points that I mentioned in detail. Now, I would say that broadly, those 2 points can be further divided into these 4 topics, these 4 concrete groups that we're pursuing in our lab. So that's symmetries, similarities, and conservation laws in continuous control, anti-redundant situational awareness for wireless visual sensor networks via feedback, predictive, robust, and adaptive online planning in stochastic environments, and adaptive resource allocation, sequential decision-making with uncertainties. So I like to categorize them into these 4 further parts. And our lab, I like to categorize the members of our lab based on the topics that they're working on. So we have a total of 14 graduate students and 3 interns who are working on this project. Okay, so out of the 4 categories that I mentioned before, I'll only talk about 3 of them for the sake of time. So I'll let the videos play a little bit, but the 3 that I'm going to talk about are the symmetries and conservation laws for continuous control, distributed feedback systems, and predictive, robust, adaptive online planning for stochastic environments. Okay, so let's start with the first subtopic. Now, here's the motivation. Most machine learning algorithms, as you probably know, are sample inefficient and over-parameterized. And especially in sequential online training settings with multiple objectives, catastrophic forgetting becomes a big issue. Now, for example, here's the case of a robot arm. Maybe we're trying to pick up this cup, we're trying to pick up this block and put it into this cup so we can model this as like a sequence of actions to let this robot arm do it. This is task 1, and then task 2 can be like the flipped version of that. And task 2 and task 1 and task 2 are related via this kind of reflection symmetry. So intuitively, we should be able to use reuse parts of this policy and use it here for task 2 without substantial retraining. Now, what about this case? Task 1 is the same thing, except task 2 is now trying to put it inside of this rotated cup. Now, there's a rotation symmetry that's associated with the position of the goal, which is the cup here. But in most of these robotic cases, it turns out we need a little bit more data in order to get the robot arm to actually put the block correctly inside of this cup, despite us humans knowing that regardless of where the goal is, we can put the block wherever we want. So we're trying to address this kind of gap here. Continual learning is a subfield of machine learning which models this. So given a sequence of tasks, T1, T2, T3, ... we want to train a single neural network model sequentially on each task TK. So you can see that these tasks are coming in and we have this single neural network model and we're trying to map it on these parameter spaces and see where they lie relative to each other. Now, as I mentioned before, catastrophic forgetting is a big issue in continual learning settings. And the reason that happens is because the same parameters of the neural network are being used for multiple different tasks. So we want to simultaneously achieve these two goals mentioned at the top of the slide. Maximize the performance on the current task while minimizing catastrophic forgetting on all previous tasks. Okay, so just a basic example, image classification. This is what most continual learning literature is focused on. We have each incoming task being a batch of images in a single class, so apples, flowers, cats, for example. And then we determine whether it's an inlier, an image that we've seen before, or an outlier, which is an image that we've never seen before. So if it's an image that we've seen before, we would kind of put it on the same point on this feature space. Likewise, the parameter space. But if it's a different task, then maybe we have some kind of distance associated with it. We can also apply this to continuous control, so robotic learning tasks, for example. So this is just brought from the example I showed previously. We have this robot arm which wants to put this block in this cup. Maybe task 4 is the reflected version of that, and task 5 is this cup rotated 90 degrees version of that. Now, this one is a little bit more complicated than the image case because it requires combination with reinforcement learning. And also the loss function of each task depends on its reward function. You also need to collect explored states and actions in real time. So this is more often an online training scenario rather than a supervised offline training scenario that is split into sequential tasks. Okay, so here's just the combined diagram that we've seen before. What's the overall goal? Well, there are two of them for us. First, we want to develop a mathematical characterization of similarity and distance in both the feature space and the parameter space, just because we want to compare how different two consecutive tasks are, because that might give us a sense of how much catastrophic forgetting might occur. And the second one is to actually design an appropriate neural network model and training pipeline, i.e. gradient descent, so that it uses the task similarity metrics that we put forth in point 1. Okay, and of course, we always want to simultaneously achieve maximum performance on current task, minimize catastrophic forgetting on past tasks. Okay. Now, towards goal 2, we have this recently submitted paper, which is currently under review at ICML. And we proposed adaptive orthogonal gradient descent. And the idea here is that while training task k+1, the next task, we want to move in the direction which is orthogonal to the gradients of task k, while adaptively tuning the gradient vector's magnitude and the learning rate in order to maintain training stability. So here's the full pseudocode of AOGD over here, but the basic idea is that, for example, here's the parameter space. that we've seen in the previous slide. So I just took this diagram and I just made it a bit bigger. Here's the optimal parameter subspace for task K, and then maybe this guy is for task K plus 1. Now, standard gradient descent training might just directly move from the optimal parameter for task K straight towards the optimal parameter to task K plus 1 using this black vector. But that yields catastrophic forgetting. So why not incrementally move in directions that are orthogonal to the subspace of the optimal parameter for task K, so that we don't vary the gradients of the parameter for task K too much, trying to minimize catastrophic forgetting in that sense. Okay, so an example application of AOGD is with the two-link ambidextrous arm. We also tried more complex examples like several Mujoko environments like the ant and walker and so on. The goal here for this robot arm is to trace the circular trajectory with its end effector, so something like this. And maybe task 2.1 is to reflect this across the origin, and maybe we want to trace this guy instead with this new arm. And then task 2.2 might be just the direct reflection of task 1. So the results of moving from task 1 to task 2.1 are shown over here. We compared it against two standard baselines called AGEM and EWC. EWC is basically freezing the weights of the network, while AGEM is doing something with the gradient storage. And clearly we can see that AOGD manages to reach the highest reward faster while maintaining training stability. So there's not much fluctuation as it increases in the number of episodes as well as the reward. Okay. I also chose this example out of all of the examples that we did in the paper, just because there's this kind of intuitive relationship between task 1 and both task 2s. They're either related via a rotation or a reflection symmetry. Okay. So some current and future work that builds off of this. Goal 1, we are still looking into directions to do this. So how do we mathematically characterize task similarity in the parameter space so that we can naturally design subsequent tasks and things like that? So right now in AOGD, our current measure of task similarity is related to the cosine similarity metric. And cosine similarity is quite commonly used in continual learning contexts. But what we're searching for is also a reduction of the parameter space to a lower dimensional representation in the feature space, simply because this representation using all the parameters in the neural network is just way too big. So towards this direction, group equivariance might actually give us some ideas. So just to recap, we might bring back the encoder part. The encoder here is responsible for transforming all of these tasks onto a lower dimensional feature space. This encoder is commonly used for image classification tasks, but not so much robotics tasks. But I'm sure we can bring it over here as well. Okay, so I mentioned group equivariance. What exactly is it? Well, equivariance is actually a notion that stems from group theory, which is a subfield of mathematics. And basically, these are the terminologies that are commonly used. We have equivariance, which basically means that the input x and the transformed input g, comma x return the same label, whereas invariance means that the label remains the same regardless of, I think I got it backwards, excuse me. So both the input and the transformed input return the same label if it's invariant, and the transformed input returns the transformed label if it is equivariant. Okay, so a common example of this is something like image classification, where the rotated image of a dog should still yield dog label. Okay, so basically we can reduce the number of parameters by simply applying these group actions. This is also called lifting the layer and reducing the number of parameters in this sense. Okay, so how do we apply this for sequential decision making? Well, we have a whole bunch of symmetries over here, like reflection and rotation. Those are also groups. So we can ideally design some kind of symmetrizer to find out how many neural network parameters we really need in order to train these kinds of similar tasks, especially if they're related by a group action. So something like this, which I brought back over here. This is just related through a symmetric, through a reflection symmetric policy. Okay. Good. So the next point of current work that we're working on is efficient memory storage. How often should we save examples and gradients? Because a large part of the performance advantage that we got while doing AOGD and other variants of continual learning is through storing prior examples. So the replay buffer is common in all reinforcement learning contexts. That's responsible for storing the examples. But we also store the trained gradients just so that we know what we want to be orthogonal with respect to. So we need to design this filter over here because obviously there's way too many examples. There's way too many gradients to store. So we don't want to store all of them. So which ones do we pick? Now, for this example, I want to bring back one of our previous works, and that is vehicle traffic network applications. So here I brought back this pattern learning architecture because I want to emphasize that what we're using here is the prediction component, where patterns can be predicted from the traffic routine, like heavy congestion in the morning and evening weekday routines. And we can also memorize past patterns, along with their corresponding optimal light signal sequences based on the patterns that we observed as well as predicted in the future. Okay, now this takes inspiration from the human memory system. This is just a loose diagram of how psychologists categorize the different parts of the human memory system. In particular, episodic memory and semantic memory are the ones that are used quite often in reinforcement learning contexts. And there's a whole branch of literature devoted towards episodic control or episodic reinforcement learning. Okay, now how does this help us? Well, we want to extend these kinds of memory architectures to include equivalence classes of similar patterns. So how do we use those task similarity measures, approximate task similarity measures, in order to design things that we want to memorize? So here we can memorize, instead of all of these individual points as separate data entries, we can memorize these entire equivalence classes and group this as just simply experience 1. Likewise, equivalence class 2 is for experience 2, and so on and so forth. And then all we have to search through the memory are just these simple experiences. So what's an example of that applied to traffic control? Well, suppose we want to do intersection control. So we're interested in looking at the number of vehicles in each direction and lane. So for example, there are 2 vehicles in the north direction, 1 vehicle in the west, 0 and 3. So we combine it into this state representation, 2, 1, 0, 3. Then just because there's one more car over here and now our current state is 2, 2, 0, 3, by and large, our optimal control is not going to change. So we can regard these as similar patterns and just simply group them into the same experience, rather than storing them individually as separate entries in the replay buffer. Okay, so this kind of data structure modification can be taken further. We can add an additional filtering step inside the memory, inspired by short-term to long-term memory transference in the human brain. Because most frequently occurring patterns should be preserved permanently in memory. Just because something occurred twice doesn't mean that it's going to occur over and over again in the future. So really, is it worth using some of our memory to memorize that rare event? So this is addressed by adding this extra filtering step. Okay. Okay, so this leads to potential design trade-offs in computation versus memory. So what constitutes frequently occurring, and how often should we perform this filtering step? Okay, so here are just some simulation results from the vehicle traffic papers from the past. We can clearly see that adding this additional memory architecture to a multi-agent reinforcement learning context does improve the performance significantly. So this over here is the plot of the vehicles that are still inside of the network. So lower is better, and clearly our method outperforms the baselines. And it also outperforms in all of the other metrics, the congestion metrics as well. Okay, so just a brief note for the last point of current work. We also want to define relationships among the loss landscapes that are used for each task. And this is done via Noether's theorem, which is a very important theorem about conservation laws in physics. Can we use Noether's theorem to bias how we store each gradient? So just to give a bit of a diagram, we want to properly reduce the configuration space of a system via its symmetries, so rotations, reflections, etc. And then we should be able to analyze it in the lower dimensional configuration space. So this requires the notion of equivalence and symmetries. And one example of this sentence is that because every task is fundamentally using the exact same robot with the same dynamics, there are exploitable physical relationships that are present among the tasks. So for example, over here, if the cup's position is slightly off compared to the exact reflection, then that really shouldn't matter in the long term. Okay, so this is still a point of preliminary work, so I don't have too much to say about that. I'll just conclude this section with the overall current and future work that I've been showing as slides. Okay, so now I'm going to change gears and move on to the second category of work, which is anti-redundant situational awareness for WVSNs via feedback. Okay, so here's the motivation for that. The target problem is looking at distributed data gathering and decision making. Now, the common implementation for large-scale networks like these is that the higher layer leverages central units that aggregate all of the sensor measurements, and then the sensors are distributed across the environment and gathering individual measurements. So the lower layer sensors push the data uplink towards the higher layer central processor. And then the central processor aggregates those and tries to make a decision for the entire network. Okay, now there are downsides to this kind of traditional approach, namely large delays, because transmitting a lot of data uplink causes those large delays. And because of those large delays, the central processor is always processing past or outdated events. There's also data redundancy because a large number of sensors increases the likelihood that two sensors will overlap. So not every sensor needs to transmit its observation to the central processor. So the motivation here also comes from human biology. The percentage of feedback synapses in thalamic relay neurons is much larger than the feed-forward direction. So taking this inspiration, why not add a feedback communication system so that we push data downlink from the central processor to the sensors? So the sensors would then use the central processor's prediction in order to figure out what parts of its current observations it should transmit to the central processor. So that decreases the amount of data that is pushed uplink, which also decreases the delays and the amount of data. Okay, so here effectively we're also looking for patterns, and we're mostly leveraging the prediction part, as you see on the bottom left. Okay, so I just mentioned this, so we'll skip that. Here's a concrete application of what I mentioned, multi-target tracking via feedback distributed data gathering. So on the left you see is a simplified diagram of what I just showed in the previous slide over here. So you can see that the main difference comes from this feedback mechanism over here. Okay, so what's the setup? We have a whole bunch of sensors. You can see these circles over here. They each have their own sensing region, and a whole bunch of targets which are moving in the environment somehow. And based off of these positions, each sensor is communicating with the central processor and telling it where the targets are located. Okay, so here are some results that we obtained from this experiment. We want to investigate how much improvement, and performance improvement here means power cost versus mean squared error, does feedback offer. So if we include feedback, do we decrease the amount of power that is utilized by each sensor to transmit its observations to the central processor, and the mean squared error of the state that is estimated by the central processor versus the true state. So in this case, it's just trying to accurately track each target as much as possible. So as you see in this video over here, as this target is moving, this is only for one target, just for visual simplicity. And as this target is moving, each sensor lights up depending on whether it realizes that the target is present versus whether it's not. And at the bottom, you can see the communication is occurring. So every time it notices a target, it transmits, and then there's this broadcast as well, shown in the red line. Okay, so just to explain the results very briefly, feedback may not always be advantageous in terms of power costs. So this is plotting the power cost, total power consumed for across all the sensors versus time. And this gray line over here is the baseline where feedback is not included at all. So we effectively want to see for all of these different feedback hyperparameter configurations, where does it intersect? And so you can clearly see that feedback is not always advantageous. You have to tune some of the parameters in your algorithm in order to get that advantage. But when you do get the advantage, you get both the power cost advantage as well as a little bit of a mean squared error advantage as well. Okay, now this setup was all vector metadata. We're only interested in the target's position, so on a 2D plane that would just be its XY coordinates, as well as the timestamp of the measurement that was transmitted, so it's a vector metadata. So it's relatively low dimensional, so reducing the amount of transmissions won't make too much of a performance difference. What's really interesting is the high dimensional data case. So what if you had a whole bunch of sensors which are now cameras, visual cameras, which are distributed across this huge environment, and we want to transmit it to the central processor in a way which is data efficient. So some example applications include AR/VR, where we're interested in rendering high quality images as much as possible, and military applications, so surveillance and reconnaissance. So this leads us to the field of 3D environment reconstruction, which is the process of capturing the shape and appearance of real objects in 3D. It's a long-standing challenge in the computer vision community. And common recent SOTA techniques, state-of-the-art techniques, are neural radiance fields, NeRFs, which essentially predict colors of points in 3D and then accumulate the value of points in the direction of view. Now, a disclaimer here, I'm not an expert in NeRFs or 3D environment reconstruction in general, but I'm only interested, so I'm only going to talk about how this stuff relates to the distributed data gathering architecture that we are doing in our research. Okay, now NeRFs have high accuracy, and so that's why they're used quite a lot in 3D reconstruction. But they also have very low efficiency. They're very slow and computationally burdensome. On the other hand, a more recently emerged setting is Gaussian splatting, which uses a whole bunch of Gaussian approximations and then splats it onto generate an image. It has higher efficiency compared to NERF. It's at least higher than NERF. It's still a little bit computationally burdensome, but it's better than NERF. And it also has comparable accuracy compared to NERF in that the environment that it reconstructs accurately mimics the real thing. Okay, now how do we apply this to feedback architectures for wireless visual sensor networks for 3D reconstruction? So in this case, the objective of the central processor would be to try and reconstruct the 3D environment based off of all of the individual visual data that was accumulated by each sensor. And so you can see I've color-coded each of the rules. So we have the fusion rule, the broadcast rule, the triggering rule, and the representation rule. These are just the breakdown of the components that we've identified are most important for constructing this kind of distributed data gathering architecture. And here is the case where we're using Gaussian splatting. And in this case, each sensor has to do its own local Gaussian splatting as well. But because the sensors should not use too much computational energy because they're distributed across the environment and likely reliant on battery power, we should not expect it to be able to use the full Gaussian splatting model in full. So how do we effectively distill the model is also a big research question that we're targeting here. Okay, good. So now, in the last topic that I want to talk about is predictive, robust, and adaptive online planning with uncertainty quantification in stochastic environments. So, what's the motivation here? Well, our lab is autonomous control for stochastic systems. So stochastic systems is what we're interested in. In many applications that are regularly affected by uncertain environments, learning as many patterns as possible can help achieve robustness to faults. And because there's a lot of uncertainty involved, we can't obtain exact predictions, which is why uncertainty quantification or our confidence about the prediction that we obtained is going to be very important here. So here are just some simple examples like autonomous driving. Pedestrians and other obstacles are often a source of uncertainty, as well as drone flights. So in the case of drone flight, we have dynamics uncertainty because maybe it might suddenly break. The rotor might suddenly degrade and fail. Okay, so here's some work that we did for planning in non-stationary environments. These are some of the more intuitive simulations that I have. Online planning is more useful when the obstacles are able to move. And it's separated into two steps. We have offline planning from a prior global map, and then online replanning to the current local map. So here's just, I'll let the videos play a little bit. One might also be interested in maintaining path smoothness while pursuing a path, just so that we can maximize safety and stability. Okay, so the previous slide did not have any uncertainty quantification or prediction for that matter in that case. So including them about the environment, about the obstacles or the system dynamics while planning could help the tracking performance. And as I mentioned before, because there are uncertainties associated with these values that we're trying to predict, it helps to quantify their uncertainty. So how confident are we about the predictions that we're making? So here's an example where we have this true path and the predicted positions might be these black dots over here. You can see that as these dots are closer to the true path, the uncertain region about them, about each black dot, is quite small because our confidence about the black dot is pretty high. So we don't have this huge uncertainty region on it. Whereas this is the case where it deviates significantly, and so we're more and more uncertain about whether we're predicting the true path accurately or not. So there's an inherent trade-off between prediction accuracy and the necessity of uncertainty quantification. Because if you have a good prediction model, you probably don't need uncertainty quantification too much. But if your prediction model is pretty bad, then UQ will probably help you a lot. Okay. So we extended, I don't know what happened there, we extended the previous planning work to non-stationary environments to include uncertainty quantification and prediction. The current considerations and the motivation for including those two aspects are as follows. There is a computational burden when there's a dense amount of obstacles in the environment. So for example, over here, this GIF is playing while I'm talking, so that's good. Over here, we have a large number of obstacles. And this agent over here is trying to navigate around these obstacles and trying to just get to this red point. So this preliminary simulation demonstrates the dense number of obstacles, and also not all obstacles are immediately important to the agent, because, for example, if the agent is over here, then obstacles that are happening over here probably not immediately important because there's no risk of collision with them in the short term. So that means we don't need to spend too much time and energy computing high accuracy predictions for less important obstacles. So the key ideas that we have in our work preprint is to implement a diversity of prediction models with varying performance specifications. This is again an efficiency accuracy trade-off similar to what we observed back in part 2, where I talked about anti-redundant distributed data gathering. Here, for example, we have predictor 1, which might have high efficiency at the risk of low accuracy. The faster you compute a prediction, the lower the accuracy might be. Whereas if you're interested in computing a very accurate prediction, then your efficiency might be low because it will take significantly more time and energy. And of course, we need to route each obstacle to an appropriate prediction model. So that's also something that we've developed as an algorithm. Okay, now towards uncertain dynamics and fault-tolerant control, everything I talked about before is related to uncertain environment, stochastic control. What happens when the dynamics itself is uncertain? Well, in order to increase the occurrence of patterns, in this case, one can intentionally model these kinds of complex uncertain dynamics as an approximate simplified model with multiple modes of locomotion. So in this case of the drone fault tolerance control, we might have we might expect these faulty situations to occur. For example, this rotor is degraded, marked by a triangle, and this rotor is completely failed, marked with an X. And based off of that, we want to figure out whether it is tracking the path accurately. And if it doesn't, then, well, these kinds of situations happen. And our prediction is bad, then this kind of happens. Okay. Yeah. And on the left-hand side, you can see that the predicted evolution of the dynamics as failures occur sequentially over time. Okay, so another example is power grid fault tolerance. So in large-scale power grid dynamics composed of multiple subsystems like buildings, houses, and other electrical units, we want to perform disturbance rejection so that these kinds of cascading failures does not occur. If there's a power outage in building 1, we don't want it to propagate over to building 2, 3, 4, etc. So without control, this kind of catastrophic failure happens. And just to be a bit more concrete about the types of models that we're looking at, this is just the linearized swing dynamics for the power grid model that is commonly used. Okay, so why do I bring this up? Well, because we can model this using Markovian jump linear systems. And here is an example of a Markovian jump linear system. We have x dot equals ax as usual, but each of these A matrices change based on the mode that we're currently in. And what do I mean by mode? I mean one of these guys over here. So for example, in this 100 or 10 by 10, 100 subsystem grid, we might experience random link failures, and so the topology of this grid might change over time. And by our observation, we might think that it might, one of these 20 modes might happen. So there are two challenges. First is the large scaleness of the network makes centralized state estimation or control difficult. And the second is, as I've mentioned, the topology might change over time due to these faults. So in that case, how do we maintain disturbance rejection and how do we control the system? Okay, so towards the control for dynamic topology networks, this is recent work that we published at CDC. We have these kinds of phenomena. So in this case, we want to simultaneously perform mode estimation. So which topology is the network currently in? We want to understand that first, and then we can think about disturbance rejection and make sure that all the states are quickly driven to 0. So disturbance rejection, those kinds of power failures, those sudden power failures are modeled by these kinds of impulsive spikes. So we want to make sure that they hit 0 as much as possible, quickly. Okay, so this allows for a sequential identification and then control approach. But another key point is that we need to keep the system stable while the identification process is taking the time to identify the true mode. So that requires a level of robustness that we introduced to our algorithm in the CDC paper. Now, what about state estimation? Well, we have some results on that too. Just to recap, these are the challenges that we're facing: large-scale control, large-scale state estimation, as well as the changing topology. So the same challenges are also relevant towards state estimation, which is the dual problem to control. And the ideas are as follows. We want to categorize each subsystem as reconfigurable versus non-reconfigurable, depending on the common topological changes that occur in the system. And then we design local subfilters for each subsystem, depending on its type. So reconfigurable subsystem might be the topology is likely to change around that area. Faults are most likely to happen around those areas. So choosing which reconfigurable subsystems and which are not reconfigurable subsystems are also a point, are also an algorithmic consideration that we address. Okay, so those are the three main groups of topics that I would say accurately represents the type of work that we're doing in the lab. I just want to conclude with some final remarks. And in the background, you can see the two broad categories that I motivated at the beginning of the talk. Now, the autonomous future that we're currently building, as I mentioned before, is highly inefficient and unsustainable. Most problems will require infrastructure for efficient data collection and processing, because at the rate that we're going now, we're just continuously building more and more data centers and increasing more and more data and compute. Excuse me. So our lab tackles these challenges in AI-based autonomous decision-making. So this is the broad class of problems that we're solving. We're doing this by learning exact and approximate system patterns while also balancing model-based versus model-free. And we achieve this through a series of analyses and applications that I mentioned, that I gave you a brief flavor of, a brief taste of throughout the majority of the talk. So symmetries, similarities, and conservation laws in these kinds of robotic control and continual learning problems, and anti-redundant situational awareness for distributed data gathering by including this broadcast feedback over here, as well as predictive, robust, adaptive online planning in stochastic environments, where here stochastic means the uncertainty can happen either in the environment itself or the dynamics. Okay, so with that, I think I have some time for questions. So thank you for listening, and I'll conclude here. Yep, go ahead.
첫 번째 상태에서 아예 데이터를 저장하는 단계에서 필터링을 해서 어떤 데이터가 필요하고 어떤 데이터가 필요하지 않는가라는 결정을 해서 그냥 그 단계에서 삭제를 하거나 저장하거나 그렇게 하신다는 걸로 제가 이해를 했는데 혹시 맞나요?
Yeah, so the question was, just to recap in English, in the anti-redundant distributed data gathering feedback, is the responsibility of the sensor to decide what parts of the data to transmit and what to not transmit. Is that correct? Yeah, that's exactly right. So it uses a whole bunch of triggering laws, so we call them triggering rules, and it decides, it compares its current measurement, its current observation of the environment versus what it thinks the central processor knows about the environment. Because the goal is to ensure that the central processor has a good understanding of the environment. So how much does the central processor know? If it is something that the central processor does not know, then I should probably tell the central processor, this is what the environment looks like now.
기존 연구들 같은 경우에는 일단은 데이터들을 저장을 해놓고 대신에 그 데이터가 어느 정도 필요한지 어느 정도 학습할 만한 가치가 있는지 아닌지를 가중치를 줘가지고 샘플링할 때 가중치에 따라서 샘플링하는 방법 썼던 걸로 제가 알고 있는데 일단 그렇게 하는 방식이 약간 좀 효율성에서 떨어질 수 있어도 일단은 모든 데이터를 다 저장을 해두는 거니까 나중에 한 번이라도 샘플링을 할 수 있다는 그런 가능성이라도 있어서 안정성은 좀 더 높을 것 같아요.
Yeah.
근데 지금 교수님께서 말씀하신 방법은 아예 그냥 그 필터가 판단하기에 이 데이터는 필요 없다라고 판단해버리면 아예 삭제를 해버리는 거잖아요. 그러면 그 필터가 엄청나게 작동을 정확하게 해야 된다는 약간 전제가 필요할 것 같은데 그러니까 그런 안정성에서 조금 떨어질 수 있다는 문제가 좀 있을 것 같다는 생각이 들어가지고 그거를 해결할 수 있었던 방법이 있습니다.
So that's really dependent on the design of the triggering rule. You can include memory inside of the triggering rule, which is why in the diagram I put them as blocks. I'm not sure how to go back to the previous slides really quickly here, but I divided the entire architecture into several blocks so that if you have an efficient triggering rule that uses your previously stored observations and then you want to fuse them and then construct a representative measurement, and then you compare that representative measurement against the central processor's estimate, then transmit that, that's totally fine too. So I think that really depends, it's a design question. Whether you want to use memory or not, that we can totally use memory. Our framework also includes the ability to use memory, but we think of that as more like a design question rather than something that will help with the analysis comparison between feedback versus no feedback case. Yep.
보통 그 디플레이 버퍼 크기를 제한을 해두고 그 데이터 개수를 넘어가면 앞에 것부터 지우고 이런 식으로 일반적으로 하는 걸로 알고 있는데 사실 그 데이터의 최대 개수를 정해놓으면 그 이상은 안 넘어가니까 약간 그 데이터를 조절하는 것만으로도 어느 정도 데이터 에피션시를 챙길 수 있을 것 같은데 지금 연구하시고자 하는 내용이 그것보다 더 줄이기 원한다라고 하시는 것 같아서 혹시 그렇게 엄청나게 극단적인지는 모르겠지만 좀 더 작은 데이터만으로도 학습을 해야 되는 상황이 있는 건가요?
Yeah, so the question was, it seems like in common replay buffer implementations, the size of the buffer is fixed, so it seems like we don't need to worry about reducing it further. Is there any literature towards towards training on less data? And the answer to that is yes. Few-shot learning, one-shot learning, those kinds of subfields of machine learning do tackle that, and our approach is also related to that as well. And I think you raise a good point, and I should have mentioned this a bit more clearly. It's not the number of data points that we're storing in the replay buffer that we're trying to reduce, but rather increasing the sample efficiency. Just because we're storing 1,000 data points, a fixed number of 1,000 data points, we can have 1,000 bad examples. We can have 1,000 good examples, or 500 good examples, 500 bad examples, right? So changing that distribution of the fixed set of 1,000 examples is really what we're looking for. We want to make sure all 1,000 of them are really good examples. Yeah, even if the size is fixed. Yeah, thank you.
Any other question? So I have quite a few questions, but I'll try to be concise. I'll try. So thank you very much for a very nice talk, first of all. I really enjoyed it. And I'm not expert in AI, but I could see a lot of similarities between the typical control theories and then what you try to do. And the question is like addressed. When I hear the second topic, I thought the immediate thought I had was, is redundancy always there? So for example, in the data association and so on, we really need to have redundancy to see whether or not the things we see is the same.
Yep.
So that's the first question. And then second question is, what is the redundancy? So what is the kind of like exact definition of the redundancy? I think that's quite important. And you haven't really discussed how to trigger actually decision to make which is redundant, which you shouldn't look and so on. So how do you actually trigger this kind of decision? Is it like the third question with respect to the second topic?
Mm-hmm. Yeah. Yeah, all three of questions are very good questions. That's also something that we've been considering. The first point about always redundancy bad, yeah, I think in the interest of time, I did not expand upon that point, but definitely there are trade-offs between adding redundancy versus increasing efficiency. So that's like the efficiency versus accuracy trade-off. The more redundancy you have, that's law of large numbers. You aggregate more data, you can increase the efficiency, or sorry, the accuracy of your mean squared error. So that's really dependent on the design of your fusion rule, which was one of the blocks, again, one of the blocks in the general architecture that I put up when discussing the feedback architecture. Currently, because at this first stage, we were interested in comparing the effect of including feedback versus not. We used a simple fusion rule, and this is also for the multi-target tracking case where everything is vector data, so it's just Rn. In that case, the fusion rule was simply just averaging every single component that we got. And indeed, in that case, the MSC did go down with feedback because we were canceling a lot of the transmissions, and so we're aggregating less data. So there's a lot of noise that filters in. So yeah, that trade-off analysis is definitely it's been a subject of the current research, and it's a subject of continuing research, yeah. Yeah, sorry, what was your third point?
Here's some of your answers, so it's okay.
Okay.
So how do you actually trigger?
Yeah, that's right. Yeah, actually trigger, yeah. So in the case of the Rn vector data that I mentioned, so we're comparing the current measurement or a representation of what the sensor is the current measurement. So that can be either its current measurement at time t, so like y of t, or maybe some aggregation of its previous memory version, so that kind of thing. sliding window average, so maybe that's just y of t. We just take the norm difference between y of t minus what the sensor thinks is the central processor's estimate of the true state. Yeah, and then is that greater than epsilon? If it's greater than epsilon, then the central processor does not have this information. It doesn't know that the current environment looks like that. So then it should trigger. Yeah.
Okay, so the kind of like the main, let's say, thing or main direction you try to pursue seems like how to improve sample efficiency. And so, think about that. It depends on how you define the basics. So in order to see how do you improve the sample efficiency, you need to have some sort of like metric, and then how do you define the metric in order to improve the sample efficiency? As an outsider, it seems like very important. So depending on which space you are looking at, it becomes completely different. So for example, are you looking at parameter space? Are you looking at feature space? And so my kind of like question I always had was which space is better to look at?
Yeah. Yeah. That's a question we don't have the answer to either. Yeah. So we're currently investigating both at the same time. I have students working on both the feature space representation of things, trying to design task similarity measures in the feature space, and then other students who are looking at designing task similarity metrics for in the parameter space. The parameter space, I would say the sample efficiency question there, it's not really sample efficiency that we're targeting right now, but rather just decreasing the number of parameters that are needed to represent the parameter space, entire parameter space. Because right now, for example, with orthogonal gradient descent, all the orthogonal gradients, so if you have a certain number of stored gradients, then because they're all orthogonal with each other, you expect that the number of stored gradients is the dimension of the space that can be representing that task. But then the null space of that, if your parameter space is like 130K parameters, then the null space is just like 130K minus the number of vectors that you stored, which is maybe like 1,000 or something. So you can't really do any analysis in there. So we're trying to figure out ways to reduce the null space, reduce the entire parameter space. I think that's the direction of sample efficiency we're going towards. In the feature space, I would say we're just trying to minimize the number of examples that are stored in the replay buffer, and that is really done by improving the memory structure. Not only minimizing the number of examples, but as I mentioned in a previous question, maximizing the quality of each example so that we can get as much trained out of each example as possible. Yeah.
So yeah, I was thinking online learning of these things, this question becomes quite important.
Yeah.
So the immediate look, we can have these, whenever you have the data, which is orthogonal to the previous kind of like learned space, then you take it and you try to use it.
Yeah.
But the question is, if the system becomes non-linear, is it still valid? Because the kind of things we try to handle is highly non-linear, I guess, and we try to somehow like promote the linear conject theory ideas in order to like somehow improve learning efficiency and so on.
Right, yeah. I do notice right now every analysis that we're doing is linear algebra and linear control. But at the same time, all of our experiments were done with neural networks, actor-critic, policy gradients, and all of like the robot arm and all of the Mujoko environments are also highly nonlinear. So we're kind of comparing both approaches, I would say. Under simplifying assumptions of those kinds of environments, how much can we apply linear control, linear algebra concepts to map out the parameter space versus the machine learning side. And I think there are a few visualization tools for visualizing the parameter space. So we're just looking at those through a whole bunch of experiments. And then we're just trying to converge towards the middle. And hopefully we're going to get somewhere with that.
So,
Yeah, thank you.
so I wouldn't ask too many questions now, but later maybe. So
Yeah.
one question is like, typically patterns are very structured. So we define what exactly pattern means prior to whatever you try to do. Is it the same case in your study? Do you need to define the patterns?
Yes. Right now, all of our experiments so far have concretely defined patterns. For example, the vehicle traffic case. There, the state space is, again, just a vector. It's a feature vector, which includes the number of vehicle counts in each intersection in the network. So patterns there would just be that vector, and then we would compare similarity of patterns by taking the Euclidean norm difference. In the case of the robot arm and current work, I would say, we're looking at more flexible definitions of patterns through group theory, actually, group equivariance, which I mentioned. Because, for example, any configuration of robot arm that could be mapped according to a single group action. So like rotations, for example. If we have a robot arm and then we can reach from this configuration to this configuration via like a 20-degree rotation, then we would just say that those are similar patterns. Those are the same patterns. Yeah, we're looking at those kinds of definitions. Mm-hmm.
Something like a dictionary learning kind of things, I think is something you can easily implement.
Sorry, dictionary learning. Dictionary learning.
You try to create bins like all the groups, different types. You can define something, and then you can group as a dictionary. And then it's kind of like creating bins, classifying the kind of different behavior patterns and so on. It seems like very similar.
I see. I'm not familiar with dictionary learning, but I think you're right. I think it would definitely help with the like memory with equivalence classes, that slide, defining what those equivalence classes are, because that was a big concern that we had while designing the equivalence classes for that vehicle traffic application. We were basically designing them by hand as a for loop. Yeah.
So it's at the moment, symmetry and distance are defined as some sort of norm, I guess.
Right. Cosine similarity, Euclidean norm distance. We've been looking at attention mechanisms recently, but that's still ongoing work. Yeah.
Any other questions? If not, please give big hands to
Okay, thank you so much. Yeah.